Hello everyone, thanks for coming. Today we are going to do a review of our week 11th linear algebra course. So in this course, we talk about the matrix power, the difference equations. So for difference equation, we have uk plus 1 equals to a uk. So in this sense, the solution uk can be written as a to the power k u0, where ak is a matrix power. Specifically, if a can be diagonalized, a equals to s lambda s inverse, then ak is s lambda k s inverse, and we can conveniently write down uk as s lambda k s inverse u0. So each eigenvector xi that is a column of S produces a pure solution uk equals to lambda I k xi. So the general solution is a linear combination of those pure solutions. The stability of the difference equation depends on the eigenvalues lambda I. If the absolute values of all eigenvalues is strictly smaller than 1, then the solution is stable and will converge to 0 as k goes to infinity. If for some lambda I, the absolute value are 1, and for others, the absolute values are smaller than 1, then the solution is bounded and the system is called neutrally stable. If at least the absolute value of at least one eigenvalue is greater than 1, then the system is unstable and the solution will blow up as k goes to infinity. So as an example, for the Fibonacci numbers, we can use the matrix power and eigenvalues, and the eigenvalues are 1 plus minus square root of 5 divided by 2 something. So in the matrix form, we can simplify this two-step recursion into one step, uk equals to a uk minus 1. As another example, we have the Markov matrices. Markov matrices basically describe the change of the probability of a Markov process. For the Markov matrices, the entries are non-negative and columns sum to 1. We can prove that 1 is always the largest eigenvalue, and the corresponding eigenvector is the steady state. For all other eigenvalues, their absolute values are smaller than or equal to 1. The powers aku0 will approach a multiple of x1 independent of the initial state, so this is a steady state solution. The knowledge of eigenvalues of A would allow prediction of the growth, decay, or steady state behavior of uk for the general difference equation. So if we look at the continuum case, the difference equation would become the differential equation in ODE, and the solution will be u0 times EAT, where EAT, this is a matrix power. This is the exponential of a matrix. We use a Taylor expansion to define e to the power AT, where A is a matrix. The calculation law is similar to the case when A is a number. For example, EAS plus T equals to EAS times EAT. DEAT dt equals to A times EAT, where A is a matrix, and EAT is also a matrix. EAT is always invertible, and the inverse is E negative AT. Specifically, if A can be diagonalized, if A equals to S lambda S inverse, then EAT is S E lambda T S inverse, and you can prove this using the Taylor expansion formula. Finally, we talk about the complex value matrices. First of all, we review the complex number that has a form A plus IB, the conjugate A minus IB, the absolute value or the modulus of the complex number. The modulus of the square of the modulus of A plus IB is A squared plus B squared. Also, we can use the polar form to record the complex number. The length is also the modulus of a complex vector in Cn is a summation of the square of the modulus of each component. The inner product is different. For calculating the inner product, we need to first take the conjugate of one complex eigenvector and then do the inner product of x conjugate, x conjugate transpose, and y. So, different from the transpose, for the complex value matrices, we use the conjugate transpose. First, we take the transpose, and then we take the conjugate of each element. So, in this sense, we can define the Hermitian matrices. If a matrix equals to its conjugate transpose, then we call it to be Hermitian. So, for Hermitian matrix, the quadratic form XH also is always a real number. The eigenvalues of the Hermitian matrices are real, and the eigenvectors for distinct eigenvalues are orthogonal to each other. For the real symmetric case and also the Hermitian matrices, they have the spectral decomposition. A equals to Q lambda Q transpose, with Q transpose Q equals to identity, and lambda is the diagonal matrix of the eigenvalues. So the eigenvectors would form an orthonormal basis, and for Hermitian matrices, they can always be diagonalized. So in this sense, from the spectral decomposition, we can further decompose this into a summation of rank 1 projections of the symmetric matrices. Thanks for listening.